Ci siamo?
Okay, so welcome to the first talk of the Colloquium Patavina by the Department of Mathematics, Tullio Levi Civita of the University of Padova. So due to the pandemic, this is the first talk of the year and it's remote, as you can see, and we hope in fall to come back in presence. But I have to say that having the possibility to have a remote talk is also very nice, because this allows us to enlarge also the number of participants that can also attend the talk all around the world. And so we have also international students that with the pandemic they cannot be in presence. So it's very nice to have now today Marco Aurelio Ranzato, that is going to deliver a very interesting talk on the curse and blessing of learning from non-static datasets. As you can see, Marco Aurelio is currently research scientist at the Facebook AI Research Lab in New York, but as you can see from his first slide, he's actually moving to DeepMind in London. He is an expert in machine learning, unsupervised learning, continual learning, students, the topic that the pandemic they cannot working on currently, and is the topic that now is going to be covered by his presentation. And transfer learning with application to vision, natural language understanding, and speech recognition. So he's actually originally from Padova, so it's a pity that he cannot be in presence here, but we hope to have him visiting us as soon as possible. And so he graduated in electronics engineer here in Padova, and he earned a PhD in computer science at New York University under the supervision of Yann LeCun. And then after that, he spent a postdoc period with Geoffrey Hinton at the University of Toronto, and then he joined the Google Brain team in 2011. In 2013, he joined Facebook and was a founding member of Facebook AI Research Lab. He has served as program chair for ICLR different edition, New RIPS, and is actually general chair of the this year edition of the New RIPS. So he has delivered many guest lectures and tutorials in top-ranked conferences and schools. And in 2016, he has been inserted in the top 100 most influential scholars in machine learning by a minor. So it's a pleasure to have you here, Marco Aurelio. So I leave the podium to you. Please start with your presentation. Thank you very much.
Thank you, Alessandro, for inviting me, and thanks to all of you for joining today. I am super excited and honored to be here. And I have very fond memories of the University of Padova. The learnings from that time have been instrumental for my career, and I'm very grateful for the opportunities that I had while I was a student there. So it really means a lot for me to be here with you. And it is also a nice break, because these days I spend most of my time moving boxes around the house. And so as I'm moving to London, so it is nice to talk about science and be here with you. Let me see. Okay, so when Alessandro invited me, he asked me to talk actually about another topic, which is low resource machine translation. And the outline of the topic it follows this diagram, where you have some large data set, and from this large data set, you draw examples uniformly at random. And then you feed these examples to a statistical model. And so the idea here is that you want to estimate parameters, and the estimation process is an iterative process. Typically, you use stochastic gradient descent, and you find some model parameters. And the secret sauce here is to figure out a clever learning algorithms that allows you to do a better prediction than existing algorithms, right? And so this is great, and but today I want to take a step back, right? And I want to think about what are the assumptions and what are the things that make this possible. So of course, you know, you can question where is the data coming from, where is the objective function coming from. Today, I'm going to discuss another aspect, which is the temporal aspect of machine learning development. Because what we see here is a snapshot. It's a snapshot of what happens through time. And through time, you typically receive data, and you typically need to update the model as data is received. So for instance, if you do, let's say, large-scale language modeling, you want to build an application where you predict, you want to complete a sentence as you type, right? You can train using, let's say, a snapshot of Common Crawl, which is, you know, data that you get from the internet. But 6 months from now, Common Crawl is much bigger, and you may want to get the additional data, right, in order to further train your model. Moreover, the data distribution changes over time, right? So for instance, if you want to do autocompletion today, perhaps this autocompletion system will work less well 6 months from now when it is Christmas time, and people talk about different things, right? And so it is very typical for a machine learning practitioner to constantly update the model and to constantly receive data and need to adjust the model. And so the question is, how can we first abstract this and come up with a learning framework that is closer to what we carry in practice? And second, how, in terms of the learning algorithms, can we design learning algorithms that work well in this setting, that do efficient transfer learning? There is another aspect, which is that over time we get more data, but typically we also get more compute. You know, that's the Moore's law. And so as you get more compute, typically you can instantiate a bigger model, and you can instantiate a bigger model also because you have more data to train on, right? And typically bigger models generalize better. That's, you know, the learning lesson from the past 10, 20 years of machine learning applications. And so the question is, how do we do this? How do we leverage the new incoming data? How do we adapt the capacity of the model over time? And how do we do this in an efficient manner? Because of course you could every time train from scratch, but it seems a little wasteful. So you may think that this is perhaps an interesting thing to look at, but why does it matter? Is it important? And I don't know whether it is important, but I believe it is. Otherwise, I wouldn't be talking about this thing today. And let me tell you a little bit the underlying motivation and what is the long-term goal that I'm going towards. So here is a picture of how I see the state of current machine learning in a very simplistic way. So we have great success stories in lots of different domains and for lots of different applications within each domain. And for each of them, we have figured out pretty good learning modules. Okay, so we know how to train very good convolutional neural nets to do visual object recognition. We have very good transformer models to do language modeling or machine translation. We have very good architectures for speech recognition and so forth, right? But now, as data arise over time, we also need to refine these modules. So these modules now are visualized as a puzzle piece, and as you can see over time, the color changes because you need to update these models over time. And moreover, because compute, you get more compute over time, you may want to consider also training bigger models over time, right? So the model size increases over time. And so the question is, what are good principles to update the model over time and to adjust its capacity over time? And finally, really, the machine learning dream is that I got a new task, and for this new task, maybe I got some textual description, And I don't even need any training example. I can just simply put together these existing modules to solve the new task. And perhaps the only thing that I need to do is to add a small puzzle piece that has relatively few parameters to adapt to the current task. Okay, so this is a task-specific module. And so the idea is that by leveraging compositionality, I can further reduce sample complexity. And so in order to go towards this stream, we need to be able to form an abstraction that is closer to what we are interested in, which is this learning from a stream of data, and B, prototype algorithms and architectures that let us more efficiently adapt to the new incoming data and possibly also adjust capacity. So that's why I've been looking at this problem. And I think if we, this is, you know, admittedly, all this talk is about more the problem more than the solution, but hopefully this is still enticing to you. And so the, as I said, data sets are not static, and there are profound implications of that in the sense that at the foundation of all the success of deep learning and machine learning over the past 20 years is the application of empirical risk minimization, the fact that you can draw IID samples from your very large data set to update your model. But now if the data comes as a sequence, you cannot go back really, or I mean, you could, but it means that it can become very expensive because you need to train from scratch on the aggregation of all the data sets that you have seen so far. So now, since data comes as a stream, data is not anymore IID. And so there is the question of what does it mean to generalize? How do you optimize in this setting? How do you transfer knowledge? And at the same time, if we make progress in this direction, it would be great, because by considering the fact that in order to solve this task, I can reuse the knowledge that I acquired from the previous tasks, I can be much more efficient, right? And this is closer to, well, you know, takes us closer to our end goal. And data sets are not static, so are models, right? Because, you know, as data arise, you want to update your model, you want to grow it. And what does it mean, you know, to optimize a model that has already converged on perhaps data from the same distribution, right? So there are a lot of interesting questions here, but again, I feel that this is a great opportunity and a great research avenue, and eventually is work in this area is a step towards machine learning, more like a software engineering business. Like, you know, we have GitHub. Whenever I want to solve a new task, I go on GitHub and I download routines that are useful and I combine them to solve my new task. I would like to do the same with machine learning, where I would like to have a GitHub repository of neural net modules that I can borrow to solve my new task, and I would like to be able to contribute new machine learning modules. And in order to do that, I need to be able to work in this sequential setting and to understand how to modularize computation and how to grow capacity. Okay, so here, this is the motivation. And now the talk is going to focus on two cases. Well, I don't know if I have time to go on the non-stationary case, but I will consider the case of that you receive a sequence of data sets. At the beginning, each data set is going to come from the same underlying distribution, okay? And I'm going to discuss what metrics we can use in this setting. I will discuss some simple baselines and provide some very preliminary experiments of what we can do with current techniques, okay? And if we have time, I'll also discuss the non-stationary case, which is the continual learning case. And needless to say, this is very much work in progress. It's very much out of the oven just now. And so there are many patches, and the point is really not to point to a solution, but to engage in a discussion and to receive your feedback, really. All right, so typically, if you think about online learning, we assume that you receive data through time. It's an infinite stream of data. And you see, and at the same time, you have a model that keeps updating on the data that you receive. But there is the assumption that the rate at which the data arrives and the rate at which the model updates is the same, right? So things are in sync. Here instead, I assume that the model converges much faster. And so the interval between two consecutive data sets is much bigger than the time that it takes for a model to converge, which means that you can do several passes over each data set if you wish, okay? And usually that's a good thing. And each data set is large enough to support training. And so if you train with some variant of stochastic gradient descent, you can think that each data set is composed by many mini batches. And so I call each data set also a mega batch to contrast with a mini batch, okay? And so for now, each mega batch has examples that come from the same underlying distribution. So there is, the I and the J contain data that come exactly from the same distribution. We assume that, yes, let me just stop here. And in terms of what we want, we would like a model that achieves low error rate at any point in time. And we would like a model that that is able to have to decrease the error rate over time. And we would like to achieve this with in a way that is efficient in terms of memory and compute usage. So the first two properties, the one that says that the model should achieve low error rate at any point in time and should be able to improve its performance over time, is the defining property of anytime learning. And so this is an instance of that. And this was proposed pretty much 30 years ago. But in this setting, I'm actually not interested in the anytime performance while learning on each mega batch. I assume that the convergence time that is negligible. But what I'm interested in is at the level of the stream, where the time tick is, this sequence of mega batches. Okay, so not at the level of the mega batch, but at the level of the stream. And so to make things clear, let me provide a toy illustration of what I mean. And so typically today, if you, let's say, work on large-scale language modeling, the time between two consecutive mega batches could be 6 months, right? And so the standard approach that people use is fine-tuning. So every time a mega batch arrives, you fine-tune, which means that you train on the new mega batch a model that is initialized from the parameters of the model trained on the previous mega batch. Okay, and the learning curve here looks like a staircase because, again, I assume that the convergence time for each mega batch is negligible. But be assured that we take that into account because we are going to report also compute and memory. Okay, so it's not that computation is free. And so that's greedy fine-tuning. Another approach is to say, I'm going to wait to aggregate a lot of mega batches to form a very large data set. And then once I have the very large data set, I train a very large model. And so that's what I call the tardy fine-tuning, which is really tardy learning, where you wait for to accumulate, let's say, m mega batches, and then you train a large model there. And so this is typically giving a much lower error rate at the end, but for the longest time, the error rate is very high. So in terms of anytime learner, both of these approaches are not great, right? Because if you look at the overall trajectory, greedy fine-tuning is a little bit too greedy in the sense that you don't account for the future megabatches very well. And the tardy fine-tuning is not very good because, you know, for the longest time, it was a terrible predictor. And so perhaps looking at the final error rate is not the greatest way to compare two different models. And in order to consider the overall learning trajectory, we consider the area under the curve. Okay, so we look at the area. So this pink region is the area under the error rate curve for the tardy fine-tuning model. And we compare this area to the area that you get when you use the greedy fine-tuning model. And of course, because this blue area is less than the sum of these white areas in this part of the graph, even though the greedy fine-tuning is a worse performance at the end, you may want to prefer greedy fine-tuning than the tardy fine-tuning. Now, can we do better? So it seems that the greedy fine-tuning, the tardy fine-tuning are a little bit at the two ends of a spectrum, but you could also update your model at an intermediate frequency. And so this is what you see here again with this yellow line. Again, this is totally made up. Later on, we'll see real experiments, but it's just to kind of justify the metric and provide an intuition at this stage. And so with the yellow line here, it's exactly like the greedy fine-tuning, except that you accumulate 2 megabatches before updating the model parameters, and therefore you're going to get a performance that is in between greedy and tardy fine-tuning. Another thing that we consider is to grow capacity over time. So you could have like the yellow model, but at time t4, you may decide to somehow, and I'm going to provide an example later, to increase model capacity, because at this point you have seen a lot of data. And by doing that, perhaps you can lower the error rate, and therefore overall you have a lower area under the curve. Okay, so that's, so far this is a conjecture. We are going to validate later, and we'll see that in some cases this is what happens, in some others not. But error rate is just one important axis of evaluation. Other important axis is memory usage and compute. So of course, for the same accuracy, for the same error rate, we would prefer models that have a lower memory and compute. And so we do very much the same thing, except that we replace on the y-axis error rate with memory and compute, report the same curves, and then compute the area under these curves. And then the smallest the area, the better the model. And of course, different models are going to strike different trade-offs at the end. So to summarize, the setting is as follows. We take a data set for the purpose of prototyping models and understanding this learning setting. We take an existing data set, we split it into capital B disjoint megabatches, let's say 100, okay? And then we loop over the order sequence of megabatches and we do just one pass. Now, the model can do several things. For each megabatch, it can loop as much as it wants to in order to update its parameters. And the more is going to, and the compute is going to be reported at the end as part of the area under the curve for the compute, right? The model can also extract from the megabatch a validation set in order to do cross-validation. So the cross-validation is done at the megabatch level. And the model can decide how long to wait before updating its parameters. It can decide not to update at every megabatch, but it can do every M or to wait until the very end. And as I said before, the metrics are area under the curve for error rate, memory, and compute. Now, let's talk about models. So we consider very simple models, those that have fixed capacity and those that have a growing capacity, and also ensembling, as we'll discuss later. Now, for the baseline model, the basic model that we consider is a mixture of experts. Okay, so this is a very old approach where in the simplest setting where you have just one layer, you have the prediction. This f of x is actually a weighted sum of experts, these h functions that are denoted with this blue ellipses here. And you have, in this case, k experts. In the figure, k is equal to 2. And this g function is a gating function that is also a function of the input x. And the j component is a scalar. And so you just take a weighted sum of the output produced by each of these experts, and the output is this weighted sum. And when it was proposed, people were trained with EM. These days, people train by standard backpropagation. If you have one layer, the interpretation is very simple. Essentially, you take your feature space, and the gating function partitions the input space into regions, okay? And you have an expert taking responsibility to predict for all the points in a region, right? So it's like a clustering, a soft clustering of the input space. Now, we stack several layers of like this, and so essentially then you're going to have a partition where you have the same expert can be applied to the second layer is going to be applied to different clusters at the first layer, and so there is a lot of parameter sharing. So the good thing about this is that it is modular. So if you go back to what we discussed before about the dream to have a machine learning system that is modular and composed by modules, experts are our modules. It is computation efficient if you do hard gating. So if you select only the expert that has the largest probability, then it really doesn't matter how many experts you have. The computational cost is always the same, right? Regardless of how many parameters you have. And so here is very appealing to use a hierarchical mix of experts, because as you add experts at each layer, the compute time is constant. But the goodness comes also with some pain, in the sense that it's very hard to train. It's very hard to get all experts to be used evenly. And of course, there are a lot of people trying to figure out how to design architectures that are more effective. But for now, let's stick to this model. Okay. And so the question is, how can we add experts, right? So at some point, we may decide that we need to add an expert. How do we do it? So the guiding principle is that we would like these experts to, let me check the chat. Can they, okay, it seems, okay. So how can we add these experts? So the guiding principle is that these experts should be, when you add the expert, you don't want to, you want to make the process, you want to keep the process differentiable, right? So if you simply add an expert by saying, I want to introduce a new expert, and let's say I copy the parameters from an existing expert, and I just add an extra output unit to the gating function, that is not going to work. And it's not going to work because as you add an extra output to the gating function, you're gonna, because of the normalization, you're gonna change also the probabilities of the existing experts. And so the loss before and after you add an expert is not going to be the same. And you're gonna see then when you optimize a jump in your loss function. And this is not something that is very desirable. And so the way that we, and so now I'm going to explain in a few minutes how we do it. And so what you care about is when to expand, what you want to expand, right? And how you expand. So I'm gonna go over each of these items. So we are trying to keep things as simple as possible. And so in the experiments that I'm going to talk about, we are going to expand every m megabatches, okay, where m is a hyperparameter. And then, but of course, you could do also better by using the validation loss. In terms of what to expand, so the idea is that we want to, if you remember, the mix of experts is partitioning the its input space into clusters, right? Soft clusters. And so the idea is that you take a cluster and you want to split this cluster in two subclusters. And now the question is, which cluster should you pick? Which expert should you split into? And so the guiding principle here is to look at the total loss and to understand what is the contribution of each expert to the total loss. And so you go over your validation set, you have a bunch of examples, input 1, 2, 3, 4, and so on and so forth. And let's say that we are looking at the contribution of the total loss of the first expert in the first layer. You go over each example whenever, and let's assume that you do hard gating, so you do hard selection of the gating also at training time. Let's say that for the first example, you pick the first expert. What you could do is to draw a lot of examples, so a lot of trajectories for the following layers, and you can average the loss to compute what is the contribution of the loss when you use this expert, and then you can average across examples, okay? In practice, we do just one sampling. So we draw one path through the sequence of mix of experts, and whenever we use this expert, we report the loss, okay? And we keep doing this. Also for the third input example, we use this module, and therefore we add the corresponding loss function, and so on and so forth. So at the end, once you have done this over the validation set, then you need to, in this case, you have two experts, and you're going to pick the expert that has the largest cumulative loss. In this, for instance, if loss 1 plus loss 3 is bigger than loss 2 plus loss 4, you're going to select this expert to split, okay? And then when it is, let's say that the expert to split now is this blue box. What you do, you introduce a new expert and you copy the parameters from the previous expert. So these two have the same parameters, are initialized the same. And for the gating function, we take the output node and we make it an internal node, and we introduce a new gating function for the two children that refer to this expert and the newly introduced expert, okay? And so as we grow, we build a binary tree, okay, for the gating, and the parameters for the newly introduced right and left child are random, which means that, again, if you think about it, the mix of experts are doing a partitioning of the input space. You take that partition that contributes the most to the loss function, and you do just a random partitioning. And then from that point on, by propagation, we figure out, you know, how to adjust the parameters and how to best move points from one expert to the other. And because we copy parameters, because of this tree structure, the loss before and after, right after an expansion step is just the same. So the process is fully differentiable. Okay, I hope this was clear. It's a little hard to understand without seeing the audience, but you can ask me questions later. And this was very much what was proposed also in this newspaper from '96, except that here we have multiple layers of the same idea. And so let's see what happens on MNIST. So here we took MNIST, we divide MNIST into 100 megabatches, and we consider a 3-layer fully connected neural net and different variants of mix of experts. So let's take a look at what happens here. So here we have on the first row the test error rate, the second row is the memory, and the third row is the compute at test time. The last row is a spider plot that shows a cumulative error rate, area under the curve for memory, compute, at training and test time. Okay, so that's a kind of a summary. But let's look at the first plot first. We have two classes of model. We have the fine-tuning that doesn't grow, and the red curves are the fine-tuning that grows. Okay, so you can think that they're all mix of experts, except that the blue line are using just one expert, and that's fixed throughout training, while the red line starts like the blue line, but over time we add experts. And notice that the y-axis is in log scale, so the growth is linear actually. Okay, and so you can see that in terms of memory and compute, the growing model require more memory and compute as time goes by. But if you look at error rate, you can also appreciate that the red curve achieve lower error rate, and also you got a better area under the curve for the red curve than the blue curve. So growing is better in terms of error rate, but you pay a cost in terms of memory and compute, as you would expect. Then the style of the line defines the waiting time. So the dotted line is when you update your model after every mega batch, okay? And the dashed line is when you do that after 5 mega batches, and the continuous line is when you wait until the very end in order to train your model. And so all these models start from the same size, so the backbone is the same, but when you grow, you keep adding experts at the layer 1 and 2, okay? And so what you see here is that the dotted line is above the dashed line for the both blue and red curve. So meaning that using intermediate rate of update is better than the two extreme, you know, the greedy fine tuning and the tardy fine tuning that I mentioned at the very beginning. So now I add other two columns that correspond to bigger hidden state size. So the first column was using 4 hidden units only, and then actually I can see, but I think it is 8 and 32. And so the obvious thing happens, which is that as you make the model bigger, performance gets better. You see all the curves shift to the lower right. And the gap between the blue and the red curve, which is between the fixed and the growing model, gets smaller and smaller as you make the model bigger. So of course, as you move from a regime of underfitting to overfitting, growing doesn't give you more and more marginal gains, eventually none. And finally, something that is quite interesting to observe is that if you look at this red dash curve, okay, and if you look at the red dash curve for the large model and for the tiny model, you can see that the tiny model that grew eventually ends up with the same amount of parameters as the big model, big model that grows, but after just seeing 1/20th of the whole data set. So the error rate is the same, right? It's roughly the same, but the big model has seen only 1/20th of the data set, while the tiny model that grew saw the whole data set. They all use the same amount of compute. They all use the same amount of memory at this point, right? And so this is quite interesting. It says that large models are more sample efficient, right? Because for the same amount of memory, you're seeing only 1/20th of the data set and you get the same performance. And so this is very much in line with recent findings from other people working on large-scale language modeling, where they show that if you have a very large model that is more sample efficient, even if you are seeing less examples, you can get to the same or better, in this case, error rate. And so this is true not just for transformers, for very large transformers, but it seems to be true also for fully connected nets in the vision setting. And we have seen the same also on other vision data sets. So this is quite typical. Well, so let's see how much time. Okay, so let me skip. So this is kind of tree view. It shows at the first layer what kind of clustering is made by the mix of expert, and it makes the clustering that you would expect, where experts are handling subset of data points with a coherent class distribution. That's fine. So on the CIFAR-10, we do this very same thing, except that we change the architecture to a VGG19, which is a convolution neural net. And the finding is very similar. Here, the only thing to add is that we compare also against Firefly, which was a method introduced in NeurIPS 2020. And this approach is quite different because they increase dimensionality as they increase capacity, which is more powerful, obviously. And they do slightly better in terms of error rate at a higher computational cost. So again, it seems that there is not so much difference between different approaches to grow at present, but they strike slightly different trade-offs. And in terms of the conclusions are very similar to what we have seen for MNIST, where bigger models tend to generalize better and to be more sample efficient. And if your model is relatively small, then you benefit more from growing. As you can see here, the red line is always below the blue line. And on CIFAR-10, you have more pronounced difference between the different rate of weight update. Different rate of update for the megabatches. So waiting every 5 megabatches is much more beneficial than training after every megabatch. We also compare the tree model on CIFAR against the flat tree structure for the hierarchical mix of experts, this light blue line. And so if you were to add experts in the non-differentiable way, where you simply add outputs to the gating function and have a flat tree structure with one layer, you actually do quite a bit worse than if you were to build this binary tree, at least on CIFAR-10. On MNIST, the difference is much less pronounced. And we also compare to ensembling, which is this blue line. So here in ensemble, you train an independent model after every megabatch, and you simply average all the these models up to now. So at this point, you average over 6 models that have been trained each on independently on each megabatch. And so as you can see over time, you do better, but it's not as good as if you were to grow the mix of experts. Okay. And the last experiment that I want to mention is the large-scale language modeling, which is much more interesting because that's the practical application here. So in this case, the data comes from Wikipedia, Common Crawl, and books, and we have 4 megabatches. Each megabatch has 440 million words. And we use a switch transformer, which is a transformer where after the self-attention layer, you have typically 2 fully connected layers, and that's where we introduce the mix of experts, where they introduce the mix of experts. And in this case, because of the large-scale experiment, we use the flat tree structure for the gating, and we had 2 experts at the time. And the finding is, again, very, very similar to what we have seen before, where if you look at the first row, here is the fine-tuning, where after every megabatch you fine-tune, and here the perplexity gets lower. Perplexity is the exponential of the negative log prob for predicting the next word given the context. And so you can think of it as the average number of words that you are unsure when you predict the next word. So the lower is better. Of course, you can never get to 1 because there is uncertainty in the data. So the task is, if you have the sentence "the cat sat on the mat," you want to predict sat given the cat, right? And so there are many things that you can put after the cat. And so the bigger the model, the lower the perplexity. And as you fine tune, you decrease perplexity, which is a good thing. If you consider the growing mix of experts, starting from the same baseline here, if you have 2 experts, you definitely improve perplexity compared to the fine-tuning model. But if you were to train from scratch, right, on the concatenation of the first 3 or first 4 megabatch, you would do even better, right? So there is still quite a bit of work to do in order to close this gap. And the gap gets, the improvement of growing becomes more marginal as you make the model larger, as we have seen before. So the conclusion is very much similar. And likewise, these models that are bigger and that you train from scratch are also more sample efficient, because they get to this perplexity with less weight updates than this model here. And so I think I need to close here. And I want to close by saying that here the idea is to come up with an abstraction of a learning framework that is closer to what machine learning practitioners experience every day, where they observe batches of data once in a while and they need to update their model. They need to increase capacity potentially. And the question is, how do you do this efficiently? And, and let me skip this for the sake of time and just go to the conclusion. And so in this talk, I propose some metrics and some simple way to repurpose standard datasets to study this problem. I propose some simple baseline for how to grow, but obviously there is much more work to do in order to make these approaches more effective. And the idea is really to go towards a machine learning, towards the dream of machine learning as a modular architecture where you can plug and play different modules and nicely grow capacity in a way that makes learning new tasks much more sample efficient and more also computation efficient. And of course, what I discussed relates very much to continual learning. So in this case, the distribution was stationary. If you make the distribution non-stationary, then we go to continual learning very naturally. It refers to other transfer learning techniques. It refers also to AutoML. In AutoML, you want to predict the architecture, the learning algorithm. But usually that's a very inefficient process because the search space is very large. But now if you account for the fact that you may have seen similar tasks in the past, you may be able to restrict the search space. And so the question is, can we make a continual version of AutoML to make it more efficient? This also relates to neurocausal learning. So there is a whole community looking at how to make predictions more robust to changes in the environment, to changes in the data distribution. And one way to achieve this is by modularizing learning and figuring out a combination of modules that makes the output distribution more robust. And that's very much also what we are doing in a way. So with all that said, I would like to thank you for joining me today. And I would like also to thank my collaborators, in particular, Tom, who is graduating in 3 weeks at the Sorbonne University, and Lucas, who is graduating at the end of the year from McGill, and also the other collaborators of mine from Facebook AI Research. So thank you.
Thank you very much. I will applaud for everyone. So thank you very much for your talk. So I have already a couple of questions. So I'll ask who can write on the chat and also to talk, because we have also some audience that can also ask the question directly. I start with the first one that is asking if we can connect this line of research with federated learning, where models have to be locally optimized using the local data sets and then aggregated globally.
Yeah, so here there is the temporal aspect, right? It's very much like federated learning. You have a bunch of local models that eventually need to be assembled. In my case, I have been looking at the temporal aspect of this process. So the fact that you have local models, but you have different local models at different time, and you need to combine them perhaps for solving a new task. So I think you could imagine also to have a federated learning that evolves over time. So what happens if you have a federated learning, that this bunch of local models that need to be assembled to produce the final prediction, but now you have also temporal aspect to it. And so the question is, how do you update each local model to integrate the new information that is coming from the new megabytes of data that you received? And so I think these two things are related, but also they are composable in the sense that you can have a continuous version of federated learning, which I think would be a very interesting direction.
Okay, then there is a question which is a bit technical. So he's asking, first of all, he's thanking you for the presentation. And then he's asking whether the updating is done over all the weights or only on some of them when increasing the module. I asked this given that you mentioned transfer learning, but I did not get how and if it relates with the proposed framework.
Yeah, that's a very good question. So in the experiments that I presented, we actually update all parameters. We don't freeze anything, we update all parameters. If you were, so I didn't have the time to discuss, but in the continuous learning version of this, where the distribution shifts, a good way to prevent loss of like forgetting. So the fact that, you know, as the distribution shifts, your model forgets how to solve previous tasks is to freeze parameters. But in the anytime learning setting where the distribution is the same, we just update all parameters because there is no reason to you know, hold some fixed. But in the case where the distribution shifts, this makes much more sense.
Okay, then there is one that is asking that basically you are assuming that you have enough time to train your model between the arrival of the mega batches. So, but what happens if you actually do not have enough time? Is the mixture of experts easy to train, even if you have a short time frame among the different arrivals of data?
Well, that's even more complicated. And I think, so you could imagine that you could provide to your model also at the input, not just the input, but also you could provide an additional auxiliary input that tells you how much time you have to train, what is your memory. And so, and based on that, your model can decide what to do, right? So if you have very little time, perhaps, you know, you may want to consider restricting the search space and fine tuning. If you have a lot of time, you may want to instantiate a much bigger model. So this is not what we have been doing. So again, given that, you know, every time that you do research, you need to start from the simplest possible setting and build bottom up. And but certainly that would be something very interesting to consider. We haven't done this, but I think that there is certainly literature where you do training on a budget, and so you can specify what is your training time, what is your the computer at your disposal, and based on that you can. But this is not what we have done.
Okay, so since you have also slides on the non-stationary case, I mean, I'm curious about that because it's the normal case. Now, usually, not only you have data that is coming through time, but also there is some change in the distribution. Would you be able in a few minutes to try to give some insight about that? So maybe if you have one slide that you think can be a good proxy for an explanation.
Yeah, so the thing that we have done is, let me remove this. Okay, so first of all, because we have been focusing on transfer more than just forgetting, we have been trying to have a more holistic view of the performance of the model and to measure not just average accuracy and forgetting and memory and compute, but also different axes of how well you transfer. It will take me some time to explain this, but essentially we are looking at basic ability to transfer from a task to the next. And in order to do this, you need to be in a control setting. So I think there is value in building control settings where you really can understand the different trade-offs that the models strike. And then in terms of the model, in terms of the model, we have been looking at a very simple architecture, which is again a mix of experts that you grow over time. This time the routing is not input dependent, but it is task dependent, okay? And the way that we figure out the architecture is by doing some sort of beam search in the space of ways to connect these modules. And so let's say that a new task arrives. What you do, you first find the architecture of the previous task that is best at solving the current task. And then you slightly perturb this architecture. And you, so you have a very restricted search space. And by doing that, you can efficiently find how to, which module to add. So that's the high level thing. And there isn't a clear paper from this year on this, and I'd be happy to follow up with you, but I think it will take more than 2 minutes.
So I have just a question about that. So very often when you have a stationary distribution, you have also something like a seasonal effect where you see the task that is coming back. Yeah. So can you comment on that? How do you deal with that in your architecture?
Yeah. So in this work, we assume that you're given the task ID. And so if later on you see again task one, you're going to use the architecture of task one, these blue blocks, let's say, okay? So you're going to perfectly recover. So because it is modular, right, there is no interference because we freeze parameters and you know exactly which module should be used for each task, okay? Now, if you don't know the task ID, you need to infer it. And so there should be another predictor that, given some data, predicts what is the task ID. And given the task ID, I'll give you the architecture. Okay. That would be very interesting too.
Okay.
So some of this, in the literature, there are examples of this where people, depending on which assumptions they make, they have different predictors for whatever information is missing.
Yeah. Okay. Is there any other question? Let me see. Yes, maybe yes. So does StarDFT equals to the classical offline training?
Could you repeat?
So does StarDFT equals to the classical offline training?
Yes. Yes.
Okay.
Yes, in the sense that in the sequential, when you receive data sequentially, it means that you accumulate all your data sets until the very end. You form a big data set and then you do classical offline learning on that. Yes.
And then the question is, it seems that you showed that this is actually, I mean, the performance that you can get with your approach is reaching the same level, but then you showed also that this is not true in any case, because when you have the large data set for machine translation, this is not really the case, no?
No, I think it is very much the same, right? So if you look at, where is it? Here, right? So let me do that. It's really funny because I see you. Okay. So if you look at the large network, right? The large network achieves much better error rate than the smaller network, right? And growing at this point doesn't buy you much.
Okay.
And this is very much the same as you got also on language modeling, where if you train from scratch a large model, you do better than if you grow. It's exactly the same. But the point is that, I lost you, where are you? Okay. But the point is that even if you train the largest possible model, 6 months from now, you need to train something bigger because you know that is going to work better. And so it's not that I have the solution for you right now to tell you 6 months from now how should you grow your model? Right now, what people do, they train from scratch. And what I'm saying is that in that setting, we still don't know, but we should be able to do something better than training from scratch. The current growing approaches that we know of don't quite work in that setting, but I think there is space for improvement, and we should be able to figure this out, because eventually if you have a truly intelligent agent, I don't foresee this agent to train from scratch every time that it receives data, right?
Okay. So is there any other question? No? Okay, I guess we can close here your talk. Thank you again for your
For having me.
talk. And so thank you, and hope to see you here very soon.
Likewise.
Okay. Thank you. Bye-bye.
Bye. Okay.